Okay, we're going to go ahead and start with Chapter 3, Derivatives. Derivatives are one of the main aspects of calculus. Okay, you've seen this limit before. This is our limit of the difference quotient. We've seen that it can give us slope or velocity. And all we're going to do now is give this a special name. This is what we call the derivative. So this limit quotient is the derivative of the function f at the point x equals a. And again, derivatives, these are really the kind of the foundation of all of calculus. Okay, we have our notation here. We call this the derivative of f with respect to x. You may also see this notation called f prime of x. And it turns out we have a lot of notations that really mean the same thing. So I want to go ahead and introduce you to these different notations that you might see. So here we say f prime of x, or the derivative of f with respect to x. This we would call y prime. This we would say dy dx, or the derivative of y with respect to x. This is df dx, or the derivative of the function f with respect to x. And this is ddx of x, or the derivative of f of x. And the important thing to understand with all of this is they all mean the exact same thing. These are different notations saying take the derivative of the function. But depending on the application or the circumstances behind the problem, one of these notations might be more useful than another. And just really important to point out, we have this notation, dx, that shows up a lot. It does not mean d times x. dy does not mean d times y. You can think of dx and dy as being very small delta x and delta y. So a very small change in x or a very small change in y. And dy over dx or dy dx does not mean division. Although you'll see later in the year that there are some cases where we can treat it this way, but it's important to understand that at its base level it does not mean division. It just means take the derivative of the function y with respect to x. So this is not d dx times f of x, it's the derivative of f of x. Okay, we have another definition of derivative, which it ends up with the exact same outcome. It's just another way to go about it. This is the limit as x goes to a. So x and a are getting very close to each other, of f of x minus f of a over x minus a. So you can see that the concept behind these is exactly the same. We have the limit as x gets really close to a, and we have delta y over delta x. And just depending on what function we're dealing with, sometimes one definition might be more useful than the other. Let's take a look at a function y equals f of x. We know that the derivative is the slope of the original function, so we can graph the derivative of f of x. Here's y equals f prime of x. That's the derivative of f with respect to x. From x is 0 to x is 1, slope equals 2, and it stays constant 2 all the way from 0 to 1. Notice that I filled in the endpoint because just like we talked about with continuity of functions, if we have the endpoint included in our domain, then we will include the endpoint. Same thing with derivatives. But notice I do not include the point 1 because it depends on which side we approach. If we approach 1 from the left, we have a slope of 2. If we approach 1 from the right, we have a slope of 1/3. So we can't give a specific value to x equals 1. So we use open circles at 1, meaning that the derivative does not have any value when x equals 1. Our slope is 0 from 4 to 6, and our slope is negative 1 from 6 to 9. So we had our graph of y equals f of x up above, and we're able to sketch a graph of the derivative down below. And so the thing you're always keeping in mind through this is the derivative is the graph of the slope. Okay, y equals x squared minus 3. We can actually go ahead and compute the derivative. So we have our difference quotient, we expand, cancel, and we evaluate the limit, we get y prime equals 2x. So there's the derivative. And go ahead and make some connections between the original function and the derivative. You can see when x equals negative 3, we have a slope of 0, and the derivative goes through 0. As you move to the right of the original function, the slope is positive and gets steeper, so the values increase, and you can see that the derivative increases as x moves to the right. And to the left of 0, the original function has a negative slope, so it makes sense that the derivative is negative to the left of 0. Okay, a function is differentiable if you can take the derivative. In order to be able to take the derivative, the function must be continuous and smooth. And that'll be leading us into tomorrow's lesson. And just to point out that although we will be learning how to do all of these derivatives by hand, there will come times where you are able to use your calculator, and I want to show you how to do that. Use this button right here next to the catalog, and you can scroll over and you can find the button that, that shows you the derivative. It's d box of box, and you can fill in those pieces. So if we want to take the derivative of x squared, we want to take the derivative with respect to x of x squared, hit enter, and we get 2x.